Hey everyone, my name is MrCaproni, and today I'm talking about social distancing in a given space. In particular, I'm talking about classrooms because as we return back in the fall, everyone's asking the question, how do I set up my classroom to best use the space while at the same time maintaining 6 feet apart from each student? Now, this is no easy task, but it seems as I'm looking at all of these blog posts as they pop up on Twitter, or if I'm looking at the news and watching stories they're doing about it, almost all of them use a photo that looks like this. Now, if you notice, all of the desks are almost in perfect straight lines, both vertical and horizontal, and they form like a grid-like pattern. I'm going to argue this is probably not the best way to set up your space, but we're going to look at the math behind it to really see why. Now, with that said, schools are not the only one right now looking at this problem. A lot of jobs and businesses coming back are looking at the best way to set up their space, or certain outdoor concerts or things like that are looking to see how they can cram the most people into a shared experience while still maintaining 6 feet apart from each person to keep them safe. So, with that said, let's go ahead and dive into the math of social distancing. All right, so what I've done here is set up kind of a mock classroom for us to look at. Now, if you notice, I placed a bunch of circles on here. Each of these circles represent a student. Now, why would I represent them with a circle? Because if you put the actual student in the middle of each of these circles and you give them a 3 foot radius, you're meeting that 6 feet social distancing guideline. Now, why is it only 3 feet radius? Because if I have 3 feet to the end of my bubble and someone else has 3 feet to the end of their bubble, then when we come together, that makes 6 feet between us as long as our bubbles never like run into each other. All right. So this is what it looks like to fill a space with 6 feet social distancing. You're essentially taking a whole bunch of circles and just cramming them in. Now, for that reason, in the math community, they call this circle packing. So if you ever want to dive deeper past what we're going to talk about today, you can always just Google circle packing, and I'm sure you will get a ton of hits that you can explore this topic a lot further than what we're going to look at in this video. Now, this is not a new problem. In fact, people have been talking about circle packing for a very long time. In fact, they've even made games about it, like this one right here called Circle Pack 13, where you can see the whole point of the game is to see how many of the circles you can pack into a given space. And just like most of the other things, then they'll claim how smart are you based off of how many circles you were able to fit. Now, how do you move this into the math realm? Well, what we're going to look at here is how can I take the total area of the circles, so in other words, like the required space we would need for those people, and the total area of the space we're given, and if I take one divided by the other, we can actually get what percent of the space we are filling with our required bubbles of the number of students that we have. So what we're going to do here is actually look at this picture and try to say, hey, what percent of our space is currently being covered with a bubble? And is there any way to make that more efficient? Because as you can see, each one of these kind of has like a little bit of space right here that's being wasted, all right? Now, in order to do this, we're going to do some basic math to kind of see what percent of this space is being covered. This grid-like formation that we've seen in all the pictures and that we've been talking about thus far is called square packing. And the reason it's called square packing is because each one of these kind of form a square in their little grid-like arrangement. So what I've done here is arranged all of the squares on here for you to see. And you can see that if I take any one given square, all right, and move it over here, we can see exactly what that picture would look like. Now, in reality, I only need to find the area of this guy right here that is being filled with circles. All right. Now, why do I only need to find the area of this? Because essentially what we can do is just mimic these squares throughout our entire space. And because it would fill up an exact percentage here, that would be the same percentage for the whole space since you're just repeating the same picture over and over and over again. So we're just going to find the area being filled in this space, and that should tell us how much space it would fill for the entire thing in terms of percent. So let's look at the math behind this guy. Now, there are two areas we need to find. One is the area of the whole given space that we have, and the other is the area of the circles that fill it. Now, in this case, this is really easy to find because we have a radius right here, and we're not going to fill it in. Even though we know that radius is 3 feet, I want you to be able to use this for any given situation. So we're just going to keep our radius as r in all the formulas we use today, all right? And when I'm looking at this, we obviously have a circle that has been split into 4 parts. Now, if we take those 4 parts and put them back together, we're essentially just looking at our original circle with radius r. And what's the formula for a circle? Well, it's just going to be pi r squared. So that is kind of our first formula for the amount of space being covered. Now, if we're looking at the square itself, our whole space, all right, that has a side length of r and another side length of r right here. So when we are looking at the two of them, really each side is 2r. Now, the basic formula for finding a square is you do length times width, or in this case, since it's a square, you can just square our side length. So in this case, what is 2r times 2r? Well, that's just going to be 4r squared. Now, I told you, how do we end up finding the percent of space we filled? Well, really, all we need to do is take this guy and divide it by this guy. That way, we can see what percent is being covered. And I already have that formula written out for us down here. As you can see, it has all the work I already put in, but at the end of the day, we are looking at 78.54% of our space being covered. Obviously, this is not going to be the most efficient way to fill up our little space. If it were, this would be a really lame video. Now, the second one we're going to look at, I'm going to argue, will cover up much more of our space, and in fact, it's a much more natural way of filling it. The best way I can explain it is by looking at a 12-pack of soda. In this case here, you know, when you get your soda, it's going to have all 12 of the cans there, just neatly stacked on top of each other. But as you guys all know, the moment you open this and start taking one or two out of it, because we have unnaturally crammed them into this box, the cans will naturally pour out and kind of form this instead of what they originally started as. Now, it's more natural because the circles kind of fall into the grooves of each other instead of forcing them to stack perfectly on top of each other, all right? This is going to form our next type of circle packing. Now, this is kind of just a larger grid for what that would look like. Still nothing fancy. We're going to be putting the students at the center of each one of these, all right? And obviously, it's still going to be filling up a general space that we have. Now, when we're looking at this, they call it hexagon packing because when you look at the overall photo, you can actually break it down into a bunch of hexagons. All right. Now, when we're looking at these little pieces, the little individual hexagons here, this is what we're going to find the area of. I'm going to find the area of the whole hexagon, and then I'm going to find the area of that hexagon that is covered with circles. Now, why are we doing this the same way as we did before? Well, before we were able to repeat one small shape into a much larger shape because the percentages will match up. In the same situation here, we're able to find the area of this little hexagon and the circles covering it, and then build it into a much larger shape. Why are we able to do that? Well, if you ever played with the little tessellation tiles growing up as a kid, you know that a hexagon is another one of the spaces that you can actually just pile on top of each other in a repeated pattern to fill up an entire given space. Now, with that said, we need to still find the area of our hexagon and the area of the circles that are covering it. Now, I included this little photo up here in the top left and another photo up in the top right to help us through these two calculations because this is going to be a little bit harder than it was last time. Now, when we are looking at the circles, that's going to be a little bit easier one to do right off the bat. When we're looking at the circles, I showed you what 3 of these hexagons would look like together. Number 1, so you can kind of still see the big picture. But number 2, so you can see that these hexagons are actually splitting each of these circles into 3 equal parts. So if you're wondering how much is this circle of the whole circle, it's 1/3 of the whole circle, because you can see it's always going to be cutting it in the exact same spot on each of our little tessellation hexagons. Now, what does that mean for our area? Well, how many of those 1/3 do we have? We have 1, 2, 3, 4, 5, 6. So we have 6 1/3 of a circle. So what's 6 times 1 over 3? It's just going to be 2, and we still have our whole circle in the middle. So in reality, how many circles are inside this hexagon? We have a total of 3 circles. Now, what is the formula for a circle? We can just do 3 times our original pi r squared that we had before. All right, so now we have our circles filling this space, and it's going to be filling up 3 pi r squared. Now, this is not a square, so we can't use the same area formula we did before. So we're going to have to see what is our total space of the hexagon? And this is actually the harder question of the two. Now, there are general formulas for a hexagon, but I know that's a little bit, you probably would have to Google it right off the bat. So let's just be reminded, how do you find the area of a hexagon like this? Well, remember, our general only measurement we have is this r right here. So I went ahead and split our hexagon into 6 triangles. And what we can do, triangles are easy to find. That's just half the base times the height. What we're going to do is go ahead and take our triangles, find the area of one of the triangles, and then just multiply it by 6 to get the whole thing. All right. So how do you find this? Well, remember, it's just going to be half the base times half the base times the height. So what is this right here? That is our r, all right? So that means the base of this triangle, the one we're finding right here, the base of this triangle is really just going to be 2 r's next to each other, all right? So again, formula of a triangle, we have 1/2 times the base, which is 2r, and then times the height. Now, this uses a little bit of math that you may or may not remember. I broke it down into these triangles up here and showed you the angles that you would see that it's actually going to turn into a 60, 30, 90 triangle. And there is a very basic rule that says this little guy right here, if this is a 60, 30, 90 triangle, and this is r, then this side length right here is going to be r times the square root of 3. All right. And that's just a general rule of thumb with your little 30, 60, 90 triangle. All right. So when we are doing this, it says that we have to multiply these 3 together to find the area of this whole triangle here. All right. So we have 2 times 2, or 2 times 1/2 is going to cancel this whole thing out. So we're going to be left with r squared times the square root of 3. Now, how many of these triangles do we have? We have 1, 2, 3, 4, 5, 6. So I'm going to also throw a 6 in front of there because we have 6 times r squared square root 3. All right. So now we have it. We have the area of the circles and the area of the full hexagon. So are you ready to see what the percent filled is? Well, I have that again down here. You can see all the same work we have, and you can see where I've kind of canceled things out to make it a little simple for us. But at the end of the day, what percent's being filled? 90.69% of this hexagon is being filled, which means if we fill our whole space with this type of circle packing, we're actually going to fill up 90.69% of our space instead of the 78% that we had earlier, which means this is far more effective. So where does this leave us? Well, I've given you 2 of the most basic forms of circle packing, all right? And I think we already can agree that hexagonal packing is going to be covering much more of our space than the square packing is. In fact, square packing will give us the 78.54% coverage, whereas the hexagonal is going to give us 90.69% coverage. Now, I know what some of you guys are thinking. Whoa, 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 Mr. Caproni. Your little hexagonal packing isn't going to fit all nicely into my perfectly rectangular classroom. To that, I would argue you have a lot of other objects in your room besides just students from wall to wall. Maybe what you can do is take that time and opportunity to use other objects in your room to fill those gaps, maybe with a bookshelf or with a computer, a calculator cart or a computer cart or your teacher desk. There are a lot of things to take into account when you're looking at a classroom setup than just the desks for students. So maybe that's what you're filling in those spaces. I don't know. But I would say that when I'm looking at all these photos from blogs and from news, I really hope that I start seeing staggered desks because that's going to be better utilizing the space that we have than the little square packing that we've seen in all of the different things. At the same time, this video is actually meant to pique your interest into asking more questions. Is hexagonal going to be the best packing for your classroom? I don't know. Maybe you're dealing with an odd space. For example, Crossroads Christian Church recently did an outdoor worship experience where they used this space, Yeatman's Cove. And what they did is they spaced flags apart so that people could stand or sit at the flags and still be social distance from everyone else by staying within their flag and giving a certain amount of space between each flag. So there are tons of awesome questions that can arise here. Number one, if you're coming from a family unit, is it smart to always use a circle? Maybe you could use some type of oval or something like that because you know that there are going to be groups of people that are standing as units instead of individuals. At the same time, this is not a perfect rectangle. So maybe hexagonal or square packing isn't even going to be one of the options you use. Or maybe you'll use a mix of options where you use hexagonal packaging for most of the area, but for these little small coves up here, you use something else that tends to be a little bit more efficient up there. I don't know. This video is meant to be a launch into asking those questions. Get you thinking. Start optimizing your space to be as efficient as possible. So I hope you gain some knowledge from this, but at the same time, I hope this is just a launching point for you to dive even deeper. Thanks for joining me today. My name is Daniel Caproni, and you can follow me on YouTube or Twitter at MrCaproni. Throughout the year, I'll be posting ACT practice videos and an AP class and regular Province Stat class for free. So if you want to follow me, please click like or subscribe and enjoy your day.